Elias Mert asked me to do a video on UTMs, but to provide context I began with the earlier system based on longitude and latitude. If you've seen my first video in this series, you can appreciate why people started looking for something simpler. This time I'll explain what they came up with. UTM is shorthand for the Universal Transverse Mercator coordinate system, but UTM is all you need to remember. Apparently the German military pioneered the concept during World War II, but it was the US Army that developed it shortly after the war. Here's why they bothered. Suppose you're at a Blue Army firebase and you want to unload a world of hurt on a Red Army target. To do that, you need to know the distance and bearing to your target, among other things. You can't see the target because it's thousands of meters away behind trees and hills. You do know where you are, and your spotter just told you where the target is. If you're using longitude and latitude, it's tricky to calculate an exact distance and bearing between points. The Army needed a simple system for calculating not just the locations of points, but the relationships between them. What they came up with isn't idiot-proof, but it's close. The Army started with a two-dimensional Cartesian grid, like we all supposedly learned about in school. The Army then simplified it by eliminating the quadrants where there are negative values of x or y, or both. They called the remaining x values the easting values, and they called the remaining y values the northing values. They also ditched the English system of distance units in favor of a single international unit, the meter. Let's go back to this spot, which I used as my example in part 1 of the series. Here you see the location using UTMs. I'll explain the Zone 13 part in a couple of minutes. What the UTM values are telling you is that this point is about 315,422 meters east of the 00 point for the grid I'm using, and about 3,973,208 meters north of the same point. What I said aloud was rounded off to the nearest meter. Any measurement more precise than that is expressed as a decimal fraction of a meter, like I did in writing. For hikers, location stated to the nearest meter is accurate enough and more precise than their GPS units can deliver. I'll comment about accuracy and precision in the third video. Once you locate 2 points using UTMs, the distance between the 2 points is provided by the good old Pythagorean theorem. The bearing is trickier, but all you need is plane trigonometry, not spherical trigonometry. Or, if that's too much to ask, you could even use a protractor. In other words, the Army reduced the distance and bearing question to math that soldiers might actually know by the time they left high school. Well, maybe the guy loading the cannon didn't get that far, but someone on the fire team could do the math using tools as simple as a pencil and paper and either a trig table or a protractor. Remember that this system was developed when there were no portable electronic computers to cough up the answer. People besides the military use UTMs. I've been an archaeologist in New Mexico for years, and we describe the location of a prehistoric site by stating the UTM values for the center of the site. It's the standard coordinate system for archaeology here and elsewhere because it's so straightforward. The system isn't perfect. Anytime you impose a plane coordinate system, meaning a flat system, on a curved surface like the Earth, you get distortions. For example, UTM north is usually off from true north, but the distortions are the same for everyone. If you assign UTM values to a point, everyone who walks to those same UTM values will arrive at the same point. If you determine UTM values for a target, a GPS-guided smart bomb programmed with those values will land on the target. And if you're dealing with the distances covered by cannon shells, the difference between a plane coordinate system and the curved surface of the Earth are less important than things such as wind speed and direction. To recap, the UTM system is based on XY Cartesian graphs with positive values only. The X value is known as an easting and the Y value is known as a northing. Taken together, the easting and northing specify the location of a unique point on the graph. The system uses a single unit of measurement, the meter. Let's talk some more about the distortions. The most famous plane coordinate system is the Mercator system, where the distortions are obvious. The UTM system is based on this system, but it reduces the distortion to a workable level by dividing most of the world into 60 vertical bands. Those bands have names ranging from 1W to 60W. Since all of those bands have the same W suffix, people usually just refer to zones 1 through 60. The NATO version of the system adds horizontal bands, and you can see those on this map. It shows how New York City is in vertical band 18 and horizontal band T, so according to NATO, it's in zone 18T. The rest of us don't need those horizontal bands. Instead, the thing to remember is that each W-type zone actually consists of 2 grids. One is for everything north of the equator. Again, using New York City as an example, It's in zone 18 and north of the equator, so you can describe its grid as 18 north or just 18N. The other grid for zone 18 is for everything south of the equator. There you can describe the grid as 18 south or just 18S. One way to think of this system is that most of the world is divided into a series of very tall, very skinny XY graphs stacked too high. Regardless of which side of the equator you're on, the easting values increase as you go east, and the northing values increase as you go north. Whichever approach you use for naming your grid, you need to know about the other approach because from time to time you'll run into it. For example, this map of Northern Europe refers to all of the zones as N zones. It's up to you to figure out that the map isn't referring to latitude band N, which is just north of the equator, but instead refers to the entire half of the zone in the northern hemisphere. Here's another example. If you look at this location in New Mexico, Google Earth claims that it's in zone 13S. It's up to you to figure out that the S refers to latitude band S and not to the grid south of the equator. Since New Mexico is north of the equator, it's not a big deal, but you do need to be aware that people sometimes use ambiguous designations for UTM zones. Let's apply what we've learned and look at the zone designation for this spot. 13S can mean that you're in the southern hemisphere or that you're in latitude band S in the northern hemisphere. Since I know the hemisphere I live in this case we're talking about the latitude band. Now let's look at the same place with a slightly different name. 13N can mean that this place is in latitude band N, which is the first 8 degrees north of the equator, or just that it's north of the equator. Since I know that New Mexico is not that close to the equator, this time N merely means north. By the way, this is the zone designation I actually use. In other words, you can eliminate any ambiguities in your GPS zone designation by thinking about what general part of the planet you're on. And anytime you come up with eastings and northings for someone else to use, it's important to state, at a minimum, which zone and which hemisphere you're dealing with. I mentioned that, quote, most, unquote, of the world is divided into the 60 W zones. In the polar regions, the distortions introduced by using those zones would be too great, so those two regions get their own zones. I won't bother with the details because most of us will never be that far north or south. What happens if your height crosses the boundary between UTM zones? Do you have to deal with the grid systems for two different zones? Actually, no. Instead, you extend the grid for the system where you started, just far enough to cover whatever you're doing. Be sure to check out the third and final part of the video series, since I'll have some final bits of useful information about coordinate systems.